All right, properties of liquids. These are the three properties we're going to look at with liquids: vapor pressure, surface tension, and viscosity. Now, all of these are related to the strength of the intermolecular attraction between the liquid particles. So, high or strong intermolecular attractions or interparticle attractions, uh, low vapor pressure, high viscosity, and high surface tension. So there's an inverse relationship between increasing intermolecular attraction and vapor pressure. So as we know, if I have a sample of material at a certain temperature, a certain number of those particles have enough speed to escape into the gas phase. All right, so this is what vapor pressure is built on. So at some point, a certain number of particles are escaping into the gas phase, and when the rate of return is equal to the rate of escape, we have a certain pressure over the liquid. Now, when we were dealing with gases, right, we had to deal with collecting over water, right? That was the situation where we had to deal with the partial pressure of water. We had to subtract it from our total pressure because we were only interested in the pressure of the gas we were collecting. All right, so at this point, this is what we're dealing with, right? Vapor pressure. High intermolecular attractions, we're going to have a low number of particles at a certain temperature with a lower number of particles at a certain temperature with enough kinetic energy to escape. Increase the temperature, though, you increase the number of particles with enough speed to escape. So with any material, as the temperature increases, so does the vapor pressure. So this is a curve dealing with water. Increase the temperature, increase the vapor pressure. Increase the temperature, increase the vapor pressure. Until I get to a point where the temperature is the vapor pressure of water is equal to atmospheric pressure. Right, so at 760 torr, 1 atmosphere pressure, I'd have to get water up to 100 degrees Celsius to have the vapor pressure of the water equal to the atmospheric pressure, and then we're boiling. All right, so just looking at some data, right? Increase the temperature, increase the vapor pressure. So it's a direct relationship with surface tension. Strong intermolecular or interparticle attractions, high surface tension. Surface tension is defined as the resistance of a liquid to stretching. All right, so it's the whole concept behind the drop, right? We stick our finger in water, we form a drop on our fingertips. It's resisting increasing its surface area, right? All the water particles are pulling each other back. It's also the property that certain types of insects leverage in terms of walking on water, right? They can't break through the hydrogen bonding web of water and sink in because they're not able to break that surface tension. So all the water molecules or all the liquid molecules, whatever you're dealing with, right? It doesn't have to be water, are pulling each other back with this intermolecular attraction, whatever it is. Induced dipole, 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 whatever. If you're underneath the surface, well, then you're surrounded by other water molecules or other particle molecules, and or other particles, I should say, and you're held tighter. So at the surface, this is the region where you're held weakest. Underneath the surface, this is where you're held most. So easier for a particle to escape the surface than escape from underneath the surface. So it's logical. All right, so comparing water, surface tension of water to the surface tension of octane. So induced dipole attraction. So you have a lower surface tension with octane than you do with water. So not as easy to form a drop with octane, right? It'll slide off your hand easier than water will. All right, capillary action is caused by surface tension. So we have cohesive forces, that's between the particles themselves, and then there's adhesive forces between the particles and the container, right? Be it plastic or glass. Right, and what you end up with is this crawling effect of water up the sides of the glass, say, burette. So what we're getting is stronger attractions between the glassware than the water molecules. That's why we end up with the meniscus. Whereas with mercury, all right, liquid mercury, you've got metallic bonds going on there, and that's a stronger attraction than hydrogen bonding. So you end up with stronger cohesive forces than adhesive forces. So instead of a meniscus, you get a bulge. All right, viscosity is a measure of a liquid's resistance to flow, and this is caused by, you think of like spaghetti, right? If you're trying to pour a bunch of BBs, right, they're going to pour easier than a bunch of spaghetti because the spaghetti particles or the spaghetti get all tangled up with each other while they're trying to flow. So that's what it basically is, the main driving force behind viscosity. It's how long the molecule is and how easily it gets tangled up with each other while they're trying to flow. So resistance to flow. So big particles are going to resist flow easier than small particles. More tangling going on with decane than you have with hexane. Related to the ease at which molecules move past each other. Again, there's a relationship between intermolecular force and temperature, right? So high temperature, you're going to flow easier than low temperature, right? So there's more motion, right? Less attraction. The stronger the intermolecular force, the lower the viscosity.